January 1940. At dispersal points across southern England, Royal Air Force ground crews work in near-freezing air. The grass fields are saturated from winter rain. Canvas covers are folded back from the engines of Supermarine Spitfires, the newest fighters in operational service. Each aircraft carries the Rolls-Royce Merlin 3 engine, 12 cylinders, liquid-cooled, rated at 1,030 horsepower. When idling, the exhaust produces a sharp, staccato pulse that rattles the ground equipment nearby. Fuel lines shimmer with condensation. According to maintenance logs from No. 65 Squadron, engines were routinely inspected for irregular fuel flow after dives or sharp turns. Pilots had reported sudden power loss when throttling forward too quickly after descent. The entries list the symptom as engine cut, cause unknown. At the test establishment in Farnborough, engineers repeat the pattern. The Merlin engine, mounted on a dynamometer, reproduces the fault with remarkable consistency. When the throttle is advanced during -G, the brief weightless moment of a downward pitch, fuel floods the carburetor. The mixture becomes excessively rich. Combustion ceases. The engine stalls. The limitation is recorded in the Air Fighting Development Unit Memorandum of March 1940, sustained negative acceleration not to exceed 1 second. Immediate corrective maneuver required to prevent loss of power. In combat, that second is critical. Across the Channel, Luftwaffe pilots flying Messerschmitt Bf-109s are equipped with direct fuel injection, no carburetor float chamber, no flooding. When chased, they can dive vertically without hesitation. RAF pilots cannot. The Spitfire's engine will quit. At Duxford and Big Gin Hill, instructors teach emergency procedures: half-roll inverted, gentle throttle, recovery at altitude. But under fire, precision collapses. Many early combat reports end with the same note: enemy escaped in dive. By mid-1940, engineers at Rolls-Royce, Supermarine, and the Royal Aircraft Establishment acknowledge the constraint. It is not a matter of pilot error. It is an inherent characteristic of the carburetor design, a simple float-controlled fuel supply unsuited to rapid -G. The carburetor is manufactured by the SU Carburetor Company, a subsidiary of Morris Motors. It has been reliable for years in civil engines, but war exposes its limits. Every attempt to modify it risks destabilizing the mixture ratio or overloading the fuel pump. In workshop notes dated February 29, an engineer writes, "Problem persistent under all dive angles. Awaiting directive. The directive never comes quickly. Design teams are already stretched across multiple projects: turbo superchargers, propeller governors, altitude compensators. The carburetor issue, though known, receives limited attention. It is a technical nuisance rather than a structural defect." At Farnborough, one engineer continues to examine the flow characteristics under varying G-loads. Her name appears on the minutes of a March 1940 meeting: Miss Beatrice Shilling, a carburation specialist. At this point, her role is routine inspection and measurement. No reference is made to a modification or proposal. Outside, the airfield remains busy. Mechanics drain tanks, refit cowling panels, and chalk inspection marks along the fuselage seams. Pilots pace in silence near the ready room, waiting for orders. By June, the Battle of France has begun. Squadrons rotate southward. The stall problem remains unresolved. In the logbooks, engine cutouts are still marked with red pencil. Each note is small, but cumulative, a quiet warning that technology, not courage, now defines the outcome of pursuit. April 1940. At the Royal Aircraft Establishment in Farnborough, a single hangar is marked for test use only. Inside, a Merlin engine is mounted horizontally, its crankshaft aligned with a reinforced steel bench. A large centrifugal fan draws exhaust gases through a flexible duct. The floor is stained with oil, blackened from repeated bench runs. The room hums at low frequency as the test stand comes alive. An electric starter drives the crankshaft until the engine ignites. A rising whine becomes a steady roar. Observers wear ear defenders, their notepads fixed to clipboards. The sequence begins at 0 acceleration, then at mild positive G. At each setting, fuel pressure, air pressure, and flow rate are logged manually. Miss Beatrice Shilling stands behind the control panel. She is an engineer in the race performance testing department, specialized in carburation. Her approach is precise and unadorned. She records pressure differentials using mercury columns, measuring the delay between throttle change and pressure stabilization. Each measurement is entered in ink. The experiment reproduces the failure reported by frontline pilots. When the throttle is opened under simulated negative G, the float in the carburetor chamber rises uncontrollably. Excess fuel floods into the manifold. The flame extinguishes. According to the report titled Merlin 3 Fuel System, Behavior Under Acceleration Forces, the phenomenon is immediate and total. At -1 G, engine stops in less than 2 seconds. Restart only after reapplication of positive acceleration. Shilling observes the readings with concentration. She requests the test be repeated under slightly different tilt angles to simulate various dive attitudes. A small adjustment in the float chamber geometry changes the timing, but not the outcome. The underlying issue is fundamental to the carburetor's design principle, gravity-dependent regulation. Later that week, she supervises a flight test at the Rays Aerodrome. A stripped-down Spitfire, serial K9797, is fitted with a modified observation rig. Thin copper tubes run from the carburetor to the cockpit, terminating in pressure gauges mounted on a temporary frame beside the pilot's seat. Test pilot notes describe the procedure in plain terms. Throttle advance during controlled pushover. Immediate cut. Fuel pressure spike recorded. Engine recovered after half roll. The record is filed under fuel flow, negative G observations. Each attempt produces the same sequence of data points: a pressure surge, mixture enrichment, and engine cut. Shilling compiles the curves on graph paper, pressure versus acceleration, revealing a consistent pattern. The carburetor's float valve reacts mechanically to gravity. Remove gravity, and it cannot regulate. In a short memorandum to the department head dated April 12, she writes, "Loss of power caused not by supply failure but by oversupply. The system admits more fuel than required during negative acceleration. Suggest investigation into restrictor orifice to limit transient flow." No formal response follows immediately. The Rays research queue is long, and the carburetor study competes with airframe vibration tests, armor analysis, and propeller efficiency work. Still, Shilling continues collecting evidence. By May, the Luftwaffe begins probing southern airfields. Fighter command operations intensify. The margin for technical failure narrows further. In pilot debriefs, frustration is quiet but uniform. The Spitfire cannot maintain pursuit in a dive. Each time, the same explanation appears: engine failure under negative load. Shilling's bench runs continue. She alters the feed geometry, replaces the float, and substitutes lighter materials. The results change slightly but never enough. The fundamental physics remain unchanged. A visitor from Rolls-Royce's experimental division inspects the setup. His note in the visitor log reads simply, "Observed IE test of Merlin carburation. Flooding confirmed. Awaiting design recommendation." The atmosphere inside the hangar remains professional but strained. Every test reinforces the same conclusion. Without redesign, the Spitfire's performance envelope will remain limited by its own fuel system. Late one evening, after the final engine shutdown, Shilling records a personal observation in the margin of her notebook. Restriction must be physical, not mechanical. A simple fixed aperture may stabilize flow. No official directive authorizes development of such a component yet, only the collection of data. But among her calculations, a small sketch begins to appear repeatedly, a thin washer with a central hole, drawn beside fuel pressure equations. June 1940. The Battle of Britain is imminent. RAF squadrons rotate continuously through southern sectors. At Farnborough, engineers accelerate their schedules. Within the test building, the air smells of avgas and hot metal. Oscillographs hum quietly as the latest Merlin engine completes another power run. Beatrice Shilling now leads the carburation subsection's investigation. Her task: determine a physical method of limiting excess fuel flow under negative acceleration. The directive is narrow but crucial: maintain mixture ratio without altering the basic carburetor mechanism. The latest data sheets show consistent readings. At -1 G, float displacement increases by 12 mm, flooding the jet. Recovery requires 6 to 8 seconds. In aerial combat, that is unacceptable. Shilling assembles her notes, flow equations, pressure traces, and timing data. Each page confirms the same pattern: momentary fuel surge, combustion loss, delayed restart. The solution must intervene between the fuel chamber and the jet orifice. She begins with calculation. A restrictor plate of 0.055 inches aperture would limit the transient surge while allowing normal flow under steady load. The dimensions appear trivial, but the principle is correct. She requests authorization to machine several test rings from brass stock held in the mechanical workshop. According to the RAE Carburation Trial Report No. 263, dated the 21st of June, 1940, experimental restrictor washers produced per Miss B.U. Shilling's specification. Installed on test engine for preliminary runs. The first test begins at 0930 hours. The modified unit runs through standard acceleration cycles. Pressure traces stabilize almost instantly. Under simulated -G, the fuel surge reduces by over 60%. Combustion continues. The Merlin no longer stalls. The result is verified twice more, then recorded in the official minutes: fuel flow stabilized through fixed orifice limitation. Simple and repeatable method. Despite success, the tone remains cautious. No one declares the problem solved. The modification is only a bench result, not yet tested in flight. Shilling requests immediate flight evaluation. The RAE assigns a single Spitfire and a pilot accustomed to test procedures. The component, little more than a drilled washer inserted into the fuel line, is fitted between the float chamber and jet assembly. It requires no redesign, no tools beyond a wrench, and adds less than half an ounce to total weight. On the 25th of June, the aircraft takes off under clear conditions. The test plan calls for 3 pushover dives, each steeper than the last. The observer in the rear cockpit notes: engine remains responsive under negative load. Power restored instantly after recovery. When the aircraft lands, fuel pressure traces confirm the observation. The carburetor remains stable throughout all maneuvers. For the first time, the Merlin runs continuously through -G. That afternoon, Shilling drafts a formal summary. Modification consists of a calibrated restrictor washer inserted at jet entrance. Limits maximum transient flow. Prevents flooding under negative acceleration. Simple to fit in field conditions. The design simplicity provokes skepticism. Senior staff question whether such a small part can justify an official directive. One memo labels it a temporary expedient. Another describes it as ingenious but impractical for large-scale deployment. Shilling's reply is brief. Component requires no alteration to carburetor body. Installation time, 10 minutes. To validate, she conducts repeated endurance tests, 30 continuous dive cycles at varying throttle settings. Each run produces identical results. The restrictor washer, now refined to a specific bore of 0.052 inches, eliminates the stall completely. In later recollections, an RAE engineer would describe the atmosphere during those tests as quiet conviction. No celebration, no announcement, only data logged and filed. By early July, the RAE concludes its formal trials. The findings are distributed to Rolls-Royce, the Air Ministry, and operational training units. The covering letter is typed on standard service paper. Fuel restriction device, tested satisfactory. Recommended for squadron issue under authority of Miss B. Shilling, RAE. Outside, squadrons continue combat readiness exercises. Mechanics stand beside open engine cowlings, unaware that a solution already exists, a ring of brass no larger than a coin, waiting for approval to reach the field. August 1940. The Battle of Britain is at its height. Across southern airfields, Tangmere, Big Gin Hill, Northolt, every Spitfire and Hurricane is flown to the limit. Mechanics sleep beside tool chests. Fuel trucks operate through the night. The pace allows little room for engineering experiments. Yet a small modification, first tested in the controlled quiet of Farnborough, begins to move outward. It carries no serial number, no production order, only an instruction note marked RAE Carburation Section, Restrictor Washer, Miss B. Shilling. The first consignment leaves Farnborough packed in cardboard boxes inside a military van. Each box contains a handful of brass discs, individually labeled by aperture size. Installation instructions are handwritten, one paragraph each, typed later by administrative staff. Insert washer between float chamber and jet unit. Secure fitting. Test throttle response. Shilling accompanies the vehicle herself. She drives north to Duxford, then to North Weald, carrying spares and a calibrated set of drill bits. Her journey is recorded in the RAE visitor log. Miss B. Shilling departed for field consultation, Fighter Command. At each station, she demonstrates the fitting personally. Mechanics gather around open engine bays, noting the precision of the component. The process takes minutes. Once installed, the carburetor resumes normal service. No further tuning is required. According to Squadron Engineering Report No. 51 from North Weald, dated the 18th of August, 1940, engine response improved markedly during dives. No power cut observed. Fitted washer to all operational aircraft. The improvement is immediate and measurable. Pilots returning from sorties confirm continuous engine power through negative acceleration. One entry from No. 19 Squadron states, able to follow 109 in dive. Engine remained live. In official correspondence, the device gains a formal title, RAE Restrictor Unit, Mark I. But among aircrew, it acquires an informal name, Miss Shilling's Orifice. The term circulates through mess halls and workshops with characteristic RAF humor. Despite the nickname, the component becomes standard issue within weeks. Manufacture remains decentralized. Local workshops produce washers from brass or steel stock using standard lathes. Aperture tolerance is specified at 0.052 plus or minus 0.001 inches. Each unit is checked with a pin gauge and stamped RAE. By September, the Air Ministry issues a technical order authorizing installation across all Spitfire and Hurricane squadrons equipped with Merlin 3 engines. Distribution expands through maintenance units. The implementation is silent but total. Data from the first month of combat use show a measurable operational gain. Engine cutout incidents drop to near zero. Dive recoveries occur 15 to 20% faster, and pursuit success rates improve correspondingly. Flight reports record the change with restrained precision. Engine continuous under high-speed dive. No delay upon throttle advance. Restrictor retained. At Farnborough, the RAE archives the completed study. Shilling files her final report on the 2nd of October, 1940. Objective: to prevent carburetor flooding under negative acceleration. Method: fixed orifice restriction. Result: effective. No adverse side effects observed. No patent is filed, no public notice issued. Wartime priority lists do not accommodate individual recognition. The modification enters the record as a minor technical adjustment. Within weeks, Rolls-Royce engineers incorporate the washer's principle into revised carburetor assemblies. Later Merlin versions adopt redesigned fuel systems, but the foundation remains her restrictor concept, a controlled orifice limiting flow transients. At Big Gin Hill, the station engineering officer writes in his logbook, since fitting of RAE device, engine reliability excellent. Recommend continued use. For pilots, the difference is physical. The Spitfire can now invert, dive, and recover without hesitation. Power delivery is constant, unbroken. In combat, this technical subtlety translates directly into survival. By the end of 1940, over 1,000 aircraft carry the modification. Few outside the engineering corps know its origin. Fewer still have met the engineer responsible, a woman who arrived quietly, installed a small ring of brass, and departed with no ceremony. Winter 1940. Fighter Command has endured the heaviest phase of the Battle of Britain. Airfields are cratered, hangars patched with canvas, and dispersal points reduced to mud. Yet the pace continues. Squadrons now enter routine rotation for rest, repair, and rearming. Within this structure, a technical change takes quiet hold. Every Merlin-powered fighter in service now carries the RAE restrictor washer, fitted, tested, and logged. The modification is simple enough that many mechanics install it during standard carburetor cleaning. No special tools are required, and no recalibration is needed. Maintenance reports confirm uniform performance. In the number 602 Squadron Engineering Diary, dated the 12th of December, 1940, a brief entry reads, "All aircraft fitted with Miss Shilling's device. No carburetor flooding incidents reported since installation." By January 1941, frontline squadrons begin to note the difference operationally. Test flights show no loss of power under negative load. Fuel consumption remains within tolerance. Engine reliability improves. The restrictor's performance is now statistical fact. Pilots record the effect in clipped, matter-of-fact terms. From number 609 Squadron. During chase dive over channel, throttle advance sharply. Engine continuous. Enemy aircraft lost height advantage. The note is short, technical, and without sentiment, but its implication is clear. The Spitfire's long-standing limitation in vertical pursuit has been removed. At Big Gin Hill, Combat Report number 347 records the first confirmed aerial victory achieved during a sustained dive. The pilot describes throttling forward past 0G and maintaining full power to recovery altitude. His debrief form carries a single annotation by the station engineer, fitted with RAE restrictor. Gradually, the psychological shift within fighter command becomes evident. Pilots no longer hesitate to push the nose down in engagement. Tactics evolve accordingly. The Luftwaffe's previous assumption, that a Spitfire would lose power in a dive is no longer valid. Operational analysts at Fighter Command Headquarters begin compiling comparative data. In the 6 months prior to the modification, engine cut-related combat losses account for an estimated 12% of failed pursuits. After installation, the figure drops below 1%. The numbers are not dramatic, but they represent the narrowing of a deadly gap. At the Royal Aircraft Establishment, Shilling continues monitoring correspondence from squadrons. Each report confirms stability and consistency. She prepares a follow-up memorandum to the Air Ministry summarizing field performance. The language remains restrained. No mechanical failures attributable to restrictor installation. Operation satisfactory in all recorded theaters. By spring 1941, the modification spreads beyond Britain. RAF maintenance units in the Middle East and North Africa receive crates of restrictors. Local fabrication begins at workshops in Alexandria and Heliopolis. Spitfires operating in desert conditions, often with fluctuating fuel quality, benefit from the same simple safeguard. According to Maintenance Unit 103's log, restrictors produced locally using RAE dimensions, material brass, aperture unchanged. Field adaptation successful. The washer's form remains identical, a brass disc, hand-sized, central hole precisely bored. Over time, mechanics begin engraving serial numbers to prevent misplacement. At squadron level, the device's presence becomes so universal it fades from notice. The Spitfire's reliability in high-speed maneuvers is now taken for granted. Only the technical officers remember that, 1 year earlier, the same aircraft could lose power with a single forward push of the stick. In the archives of Fighter Command, a memorandum dated April 1941 closes the matter formally. Problem of carburetor flooding under negative acceleration resolved through RAE restrictor device. No further action required. There are no ceremonies, no announcements. Wartime engineering rarely allows pause for recognition. Yet among technical personnel, Miss Shilling's name remains attached to the modification in every casual reference, sometimes written directly into engine logs. One officer at Northolt adds a note beside his inspection checklist, restrictor fitted, per Miss Shilling. Leave in place. The phrase becomes standard instruction. Spring 1941. RAF combat formations now operate under new tactical assumptions. The Spitfire's limits, once dictated by its carburetor, have vanished. The aircraft's handling remains unchanged, but its operational boundary has shifted subtly, decisively. Pilot training manuals are revised to reflect the change. The section once marked "Avoid prolonged negative G" is quietly removed. In its place, engine power maintained under all flight attitudes. Recover using throttle as required. At Hornchurch, combat instructors brief new pilots accordingly. You may now follow through a full dive, one senior flight officer notes. The engine will hold. The statement is factual, not rhetorical. No one attributes the change to any particular engineer. The modification is considered standard equipment, part of the aircraft's anatomy. From this point onward, pilot reports begin to describe a new fluidity in combat engagements. Vertical reversals, once risky, become routine. Dogfights extend upward and downward without interruption. In a letter preserved in the Imperial War Museum, a pilot of No. 92 Squadron recalls, "Before, if you pushed forward too hard, the Merlin died. After the washer, she just kept going. You could follow the 109 through the dive and stay on the guns." This capability alters German tactics as well. Luftwaffe pilots, accustomed to shaking pursuit through vertical dives, begin to lose that advantage. Intelligence summaries record the shift. A translation of a captured Luftwaffe document, dated August 1941, reads, "Spitfire engines no longer fail under negative acceleration. Dive escape no longer reliable. The modification has become an invisible equalizer." At Fighter Command's analysis section, performance data illustrate the same pattern. The average engagement altitude increases by several thousand feet. Interceptions occur at higher speeds. Mission endurance improves as dive recovery no longer requires power cycling. The numbers are understated, but cumulatively they describe a transformation. Rolls-Royce field engineers report minimal maintenance impact. The restrictor shows no significant wear, no leakage, and no measurable loss of top-end power. Carburetor life remains identical to unmodified units. According to Rolls-Royce Technical Bulletin 147, issued in 1942, i.e. restrictor device satisfactory under all operational conditions. Incorporated into new carburetor specification as standard production element. For the first time, the solution leaves the realm of field adaptation and enters industrial manufacture. The fixed orifice becomes part of every new Merlin carburetor shipped to Supermarine, Hawker, and de Havilland. Pilots notice only results. The Spitfire's responsiveness at altitude now exceeds expectation. During intercept climbs, the engine transitions smoothly even when inverted or subjected to sudden acceleration changes. The aircraft can now execute continuous rolling dives, maneuvers once avoided entirely. An RAF Tactics Bulletin, circulated mid-1942, summarizes the effect with typical brevity. Negative G limitation no longer operational constraint. Pilot confidence increased. Confidence is an understated metric, yet within the RAF it defines survival. The ability to follow an enemy aircraft through any maneuver, without mechanical penalty, alters morale as much as performance. Beatrice Shilling remains at the Royal Aircraft Establishment, supervising further engine tests. She declines transfer offers and continues her technical work without public attention. Her name appears on test memoranda concerning high-altitude fuel compensation and supercharger boost pressure, but the restrictor washer remains her most direct and enduring contribution. By 1943, Spitfire variants, Mkv through Mk9, incorporate refined fuel systems derived from her work. The same principle allows subsequent Rolls-Royce Griffon engines to operate under far higher loads without failure. Combat analysis from 1941 to 42 shows the cumulative effect in numbers rather than headlines. RAF victory-to-loss ratios improve incrementally. Pursuit engagements last longer. Pilot survivability increases. Engineers at Farnborough classify the change not as an invention but as a correction, a technical equilibrium restored. To those who record it, the detail seems minor, a brass washer smaller than a shilling coin. Yet its consequence is operational superiority measurable across an entire theatre. At year's end, an internal RAF memorandum summarizes the issue in neutral language. The carburetor flooding fault having been corrected by RAE design, Merlin engines may now be considered reliable under all latitudes. No further modification necessary. The note closes the file. There is no citation, no award. The technical officer's name remains a line item on a report. But in practical effect, the Spitfire, the most symbolic aircraft of the war, now performs exactly as intended, free from its single most dangerous flaw.